So nucleophiles are actually just Lewis bases, right? Because Lewis bases are where the Lewis base donates electrons, and that's what nucleophiles are. They just donate electrons because the nucleophile itself is unstable. So the trend for that is that this way. It's the opposite of electronegativity. So that means the nucleophile strength will increase as you go to the left and as you go down. So why is that the trend? Because as you go to the left, atoms don't really like having excess electrons, right? Because over here are where the electronegative atoms are, right? And electronegative atoms want electrons. But over here, they don't really want electrons. As you go this way, they start wanting to get rid of electrons, right? Especially over here, they start wanting to give away electrons. So that's why as you go to the left, atoms don't like having excess electrons, and that's why the negative charge will make them a good nucleophile, is then they want to give away their excess electrons. Now, the reason why it increases as you go down is because of polarizability. Polarizability increases because as you increase the number of shells, the less strength the nucleus has on the very far away electrons, right? So since the positive and negative charge interaction is so weak, the actual atom can give away its electrons, making it a good nucleophile. A good nucleophile is also better when it's sterically unhindered. What that means is that it doesn't have bulky groups next to the actual negative charge. So therefore it has a higher chance of actually attacking a electrophile. So some examples of different nucleophiles and weak nucleophiles. Strong nucleophiles and weak bases would include the halogens, and then pretty much anything having to do with sulfur. Sulfur is polarizable, so that's why it loves giving away electrons. The other thing is oxygen, right? Oxygen attached with a hydrogen or a methyl or ethyl and then having a negative charge. Those are also really good nucleophiles because oxygen, right? Even though oxygen likes having electrons because it is an electronegative atom, it'd prefer to be more stable, so therefore it can give away electrons. And finally, just examples of what are weak nucleophiles. Water, for example, is a weak nucleophile, right? Because water is pretty stable. Oxygen has 2 lone pairs, but it has 0 formal charge. So since it has 0 formal charge, it's really stable, so therefore it doesn't want to give away electrons. That's why water makes a weak nucleophile. So let's do some practice, right? So for example, this is a ranking question. Just label it from 1 being the best nucleophile to 5 being the worst nucleophile, and I'll tell you the answer. Okay, so now since you've tried that, the actual answer is 3, 1, 2, 4, 5, and let's go through the reasoning. So the first thing you look at is just the actual trend, right? So the first thing you look at is this trend right here. So after you look at the trend, then you look at different things such as induction, and then finally you look at sterics. So let's look at this one, right? So this one is number 1. Why? Because nitrogen, let's look at the first base element for each one of these. This one is nitrogen, right? Nitrogen, 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 oxygen, oxygen. So these are the electrophiles. We have nitrogen and oxygen. And the trend we know is that nucleophilicity, right? It increases as you go to the left. So that means that these 3 will be better nucleophiles than these because a negative charge on nitrogen is more unstable. So now we have to determine between these 3 because all 3 of these have nitrogen. So now what we look at is induction effects. Induction is when an electronegative atom, right, such as chlorine or fluorine, they pull away the negative charge. So what is the main purpose of a nucleophile, right? To give away. To be a good nucleophile, it has to be unstable, meaning that it wants to give away its electrons. So if it has the negative charge right here, but fluorine is pulling away the negative charge through the bond, right? What is that doing? Well, if it's making the nitrogen less negative, then it's making it more stable. If it's more stable, then it doesn't want to give away its electrons, right? So that's bad for a nucleophile. So out of these 3, this one doesn't have any halogens. Therefore, all the negative charge is on the nitrogen. So that's why this one is 1. Now between these two, this one is chlorine and this one is fluorine. From electronegativity, we know that fluorine is the most electronegative atom, and so therefore this fluorine will actually pull the negative charge away from nitrogen, right? So that will make it more stable. So, but chlorine's not as powerful, right? It's because it's lower down. So since it's not as powerful, this will be number 2, right? Because chlorine doesn't pull away as much. So therefore, most of the negative charge is still on the nitrogen, making it a good nucleophile. This one would be 3 because it pulls away a lot more than chlorine, but it would be 3 because the base atom beats the original, these two oxygen atoms. So finally, we have 1, 2, and 3, and now we have to look at these two. Well, both of these have oxygen, and now when we look for inductive effects, both of these don't have any fluorines or chlorines. So now what do we do? Well, the final thing I said was that nucleophiles are better when they're sterically unhindered. So let's look at these two, right? So in these two cases, right, this carbon, right, these two carbons, well, this one is a primary and this one is a primary, right? Over here, though, right next to that nucleophile, we have a tertiary. That means that this is really sterically hindered because we have huge amounts of hydrogens, right? Because we have 3 hydrogens on all of these, and the bigger the group is next to that nucleophile, right? The bigger the groups are, the worse it is for the nucleophile because it'll be less likely, it'll have a decreased ability to attack an electrophile because it's so big. You need the nucleophiles to be small. In this case, since it's so big, this one will be 5 and this one will be 4. So let's do one more example. So try this and then I'll explain the answer. Okay, so for this one, the actual answer is 4, 3, 2, 1, 5. So let's once again go through our logic. So we go through the base atom, right? So in this case, it's oxygen, sulfur, nitrogen, and then oxygen. So once again, nucleophilicity increases as you go to the left. Okay, so nitrogen in this case would win. But the other thing is that nucleophilicity also increases as you go down. And if you look at the periodic table, nitrogen and sulfur are actually diagonal. So which one wins? So this is kind of tricky, but in this case, the one on the top actually wins. So because as you go to the left, the negative charge makes it more unstable, making it a better nucleophile. And as you go down, it also increases, right? Because it makes it a better nucleophile because of the increased polarizability. The thing is, as you go to the left, right, if you have a diagonal, in most cases, the top one will win, meaning going to the left is stronger than going downwards. So the nitrogen will beat the sulfur in this instance. So that's why nitrogen is number 1 and sulfur is number 2, because it's just that the nitrogen is more unstable and therefore a better nucleophile because it wants to give away the electrons, rather than the sulfur, though even though it's good because the polarizability is increased, it's still weaker than nitrogen because sulfur can still handle that negative charge better than nitrogen. So if it's a competition between 2 atoms and they're diagonal from each other, the one on the top will usually win. So in this case, nitrogen is on the top, it's above sulfur, so nitrogen wins in this case. So it will be number 1 and sulfur will be number 2. Now we look at the base atom for these 3 and they're all oxygen. So we go back to the original thing, right? So we want a nucleophile to be unstable. That's the main point. Because if it's unstable, then it'll want to donate electrons. So let's look at these 3, right? So this one has nothing done to it, right? It's just oxygen with a negative charge. This one has resonance, and this one has resonance and inductive effects. So in this case, it'll be number 3, right? Because we want it to be as unstable as possible. So resonance on both of these will stabilize the negative charge, and we don't want that. Because if it's stable, then it won't want to give away its negative charge. So this one will be 3 because it doesn't have anything. It doesn't have resonance, or it doesn't have resonance and inductive effects. Now, we know that negative charge, right, resonance will stabilize that negative charge. And same thing for this one, the resonance will stabilize this too. So how do we determine between these two? Well, the inductive effect, right? So for induction, this fluorine, these three fluorines actually, will pull the negative charge away from the oxygen to the fluorine. So what it's doing is spreading that negative charge out more. And when you spread out the negative charge over a greater number of atoms, you're actually stabilizing the entire molecule. And if we have a stable compound, that's not good because we want the compound to be able to donate electrons, right? We want it to be able to donate electrons. And if it's stable, why would it donate anything? And that's why this would be 4 and this would be 5. Because even though both of these have resonance, this has the additional stabilizing effect of induction, right? So since it has the additional effect of induction, this will be more stable, and so this will be 5. I hope that helped, and thanks for watching.